Welcome friends. In today's lecture of strength of material, we are going to discuss the basic terminologies which will be useful for finding SFD and BMD, like reaction forces, finding out reaction forces with the use of engineering mechanics, rules and nomenclatures, conventions. Let us start with the stress. And after that, we will discuss the stress strain curve for engineering materials. The stress is the ratio of internal resistance offered by a material on the area on which the external force is applied. Let us see in the diagram. If a force F is applied on this area, here you can see this area. If force is applied on this area, cross-sectional area here, then the internal stress will be generated inside the material. That's internal stress. Here the internal force will be exactly equal to the F. The resistive force R will be equal to the F, because there is no any other force, and you know that where there is action, there is equal and opposite reaction. So in this case, the F will be equal to R. So our mathematical formula for stress will be applied force divided by A. Applied force, we know that we can here put R by A or equal to F by A, because here both the forces are equal. Coming to next slide. Here you can see the different types of stresses, and all the types of stresses which will be useful for finding SFD and BMD, which we are going to discuss in today's lecture. First is the normal stress. In previous slide, you have seen that if the force is applied on the normal to the particular surface, the stresses generated in this longitudinal directional or the transfer direction will be called as normal stresses. Here you can see that two types, longitudinal stress and another will be transfer stress. Third one is volumetric stress or bulk stress, which is caused because due to the volumetric strain generated. That means volumetric strain, we are going to discuss this also, what is strain and what is the volumetric strain. Because of that strain, the stress developed inside the material will be called as volumetric stress or bulk stress. The another stress which is also important, that is shearing stress or tangential stress. We will discuss these things one by one. First of all, see what is strain. Strain is the ratio of the change in dimension of body to the original dimension of body because of applied forces, obviously. When we apply forces, if there is a elongation in, let us say, this diagram, if delta L is the elongation after applying force F, then delta L divided by L will be equal to the stress, and that will be a longitudinal stress. Longitudinal strain or stress, and that will be denoted by, here you can see in the next slide. Here, let us say this is the longitudinal stress, force upon area by A. Okay. Then types of strains and their subtypes. There are main two strains like stress also. And there was shear stress and normal stress. Here also shear strain and normal strain. These are the two main types. Then normal strain is again have subtypes like longitudinal strain, volumetric strain, and lateral strain. Normal stresses can be tensile or compressive. We will see that if the forces are outward away from the center of the axis or the CG of the body, then we will call it as a longitudinal strain. Here in the first diagram, you can say these two forces will create longitudinal strain because change in dimension is along the longitudinal axis. If there is a decrease in the diameter or this area, then stress created or stress generated here will be a transverse stress and transverse strain. That means stress and don't confuse between stress and strain. Both stresses and strain will be generated. We are talking here transverse, or it is also called as lateral strain. Okay, and volumetric change or volumetric change will create a volumetric strain. As soon as there will be a change in volume, that change in volume divided by the original volume, we will get the volumetric strain. Now look at here. What are the different types of modulus which we are going to discuss? Young's modulus. First is the Young's modulus. It measures the resistance of a solid to a change in its length, that means in longitudinal direction. Whereas shear modulus is applicable or useful for measuring the resistance to the motion of the planes within a solid parallel to each other. In the coming slides, you can see here itself. If let us say, I will draw one figure. Go find the figure. And this is the component. Okay, and we are applying some tangential force here in this direction. Okay, in this direction. Then let us say this component is deformed to such a position here, like this. Now this much distance divided by the height or a component. Here you can see tangential strain will be, let us say this is the angle theta. Now here you can see here theta is the strain, and how we will calculate this theta, this angle made by these two lines, actually those are planes. We will divide this opposite side by adjacent side, because this is a right angle triangle and this is a hypotenuse. Then let us say this is a delta x, and let us say this is a L. Then delta x divided by L will be the theta. Okay. Now coming back to our slide. Let me erase this annotation. Okay. Now we were discussing shear modulus. Here it measures the resistance to motion which we have seen, the displacement of the upper surface, let us say that the motion, the resistance to that motion of the planes within the solid parallel to each other. We will discuss in details as we will go further in the slides of this presentation. Then bulk modulus. What is bulk modulus? It measures the resistance of a solids or liquids to changes in their volume. We will also discuss this in detail in coming slides. Tangential stress, you know that the force in tangential direction and the area on which this force is acting, force divided by area. This force actually a resistive force offered by the material because of application of this external applied force. So once we get tangential force, we will find the shear strain. You know that shear strain from this from a last diagram which I have drawn, you have seen that opposite upon adjacent we will get tan theta. As theta is very small, we can write it approximately equal to theta only. Tan theta equal to theta in case of it's very small angle. Because whatever the deformation will be there, it will be very minute. Even though I am drawing it to understand you very large distance on the diagram, but it will actually be very small. Now, modulus of rigidity. What is modulus of rigidity? It is related to this shear. Tangential stress upon tangential strain, or tangential stress strain is also called as shear strain. That is, even I can say it shear stress divided by shear strain, or tangential stress divided by tangential strain. It will be F by A divided by theta. We know that theta is let us say delta x by x. In previous diagram I have explained it. X is the height here, small x, and delta x is the movement of the upper surface, the uppermost surface, which is caused due to shear. Now, Young's modulus. What is Young's modulus? It is related to the normal stress and strain. Previous was the related to the shear stress and strain. That is modulus of rigidity. Here it is Young's modulus stands for Young's modulus denoted by Y. Here again the same way, stress divided by strain, we will get the Young's modulus. Any modulus, how we calculate? Actually, we calculate or get it from the stress strain curve. We are going to discuss in this slide. After one slide, just look at here how we will use these formulas, or I will explain here. You can see there here there is a stress on y-axis and strain on x-axis, and up to this point A, it is a proportional limit. That means stress is proportional to strain. That means I can write stress sigma. Let us say stress is sigma directly proportional to strain. Then if I will add a proportionality constant, that constant will be nothing but the Young's modulus, or any modulus. In case of it is a shear stress, it will be modulus of rigidity. We were discussing longitudinal stress by strain, longitudinal strain. That is Young's modulus. We have calculated earlier what is longitudinal stress, force, resistive force divided by area, F by A, and longitudinal strain is the change in length divided by original length due to the application of external force. Okay. Here we have got delta L by L, that is the strain, longitudinal strain. Now we will divide stress by strain. Here we will get the Young's modulus Y, F by A divided by delta L by L, and finally FL by A into delta L. This is Young's modulus. Actually, what exactly strain means, I have already told you verbally. Here we will see in diagram, and I will try to explain. Strain is actually a ratio of change in dimension to the original dimension of a mechanical component or any machine element, which we either using for designing a mechanical device or civil engineering structure. For example, transverse strain or lateral strain is a change in the change in the area, actually perpendicular area to the original area. That means perpendicular area to the force. Here is little mistakenly written. Change in this area, cross-sectional area, which is perpendicular to this applied force. Okay. Change in this area, let us say that is delta A, and the original area here we have given, that is A0. Then what will be the lateral strain? Delta A divided by A. Okay. Similarly, all lateral longitudinal strain, volumetric strain, and which we have seen in previous slides. Now this is the most important slide, because many times in interview question is asked on stress strain diagram. Very first point, they can ask you on which axis stress is given, or we take stress on y axis or x axis. Keep in mind, we always keep strain on the x axis, as strain is independent quantity. You may have studied in your matriculation level or 10th 12th classes. So we cannot put strain on y axis and stress on x axis. And then we will discuss all the points one by one. As I already told you, this point A is the proportionality limit or elastic limit. That means up to this point A, the material shows a proportional change in stress and strain. That means for a particular, let us say our proportionality constant is let us say 2 for example. Then at this particular point here, if you draw the vertical line and horizontal line, you are getting stress by strain equal to 2. Here also you will get stress divided by strain equal to 2 up to this limit. That means if you know particular one value either of a strain or a strain, you can find another value if you know the modulus of elasticity for that material. And it is necessary for computation, either with the help of computer or many softwares. This proportionality limit, from this elastic limit or proportionality limit, we can calculate or design any designs with very ease. Now coming to the point B. Point B is the upper yield point or yield stress point, upper yield stress point, you can call anything. That means from point A to B, even you are applying load. This stress strain diagram is actually an engineering stress strain diagram. That means engineering stress strain curve. You can see in this diagram here. Engineering stress strain diagram shows that tells that we assume that the cross-sectional area is constant for even after applying force, and there is a elongation. This is for our ease of calculation, because we engineers are a little bit easy, and it has a practical application and significance. Even there is a true stress strain curve you can draw, but for ease or simplicity of calculation, we use engineering stress strain curve, and in that we consider the diameter is constant for all over the experiment. Now, once we go on increasing the force or the applied force or load, this elongation will go on increasing, and stress will go on increasing, and similarly the strain will be go on increasing. If we will put those values consecutively on this graph here, graph paper on x and a y axis, we will get such a graph. Okay. Now let us discuss what this point A to B area indicates. This A to B is also elastic. There will be also a elastic elongation, but that is not proportional. That means the ratio of stress strain will go on varying from A to B. That will not be a constant value. Okay. Then this point C is the lower yield point or lower yield stress point. If we will go on increasing the load, there will be a plastic deformation. What is the mean by plastic deformation? Let us say from here, from this point C onwards, there will be a plastic deformation. And what is plastic deformation? That means once there is an elongation, the material will not regain its original shape and size. Okay. And there will be, we can say, change in dimensions, permanent change in dimensions. That's called plastic. And before this point C, this region from O to point C on the x-axis will be a elastic region. This is a graph for ductile material, and in case of brittle material like cast iron, the graph will be different, which we will discuss in next slide here. Okay, let us look at here first. This is the plastic. This zone is elastic zone and this is plastic zone. Okay. Here I can also explain. Here are the few points given, but not all. Okay. Point C we have discussed. It is the lower end yield stress point. Then point D is the ultimate stress point. And finally the point E is breaking or rupture point, breaking point. Okay. What are the significances of these all points on the graph? That is, we will come to know for particular stress or particular amount of load applied, what will be the deformation, and that's why the strain. So how much load should we apply on a machine component, or it can be a civil engineering structure like bridge or anything else. This is the use of this stress strain curve, and this particular stress strain curve is for ductile material like mild steel. Okay, moving forward. Now look at the stress strain curve for brittle materials. Brittle material, for example, cast iron. Now you can see after a proportionality limit, there is no such a plastic deformation, very less, and immediately the material will fail or break. Okay, the ultimate strength point and breaking point are very close to each other, and even the yield point also. So this is the basic difference in the stress strain curve of a ductile material and brittle material. Here point O to A, which we have seen in previous diagram, will be same. In brittle material also, there will be a proportionality limit, and the stress will be proportional to strain. In case of brittle materials also up to a yield point, that is point A. Here you can see. Now moving forward, the stress tensor. What is stress tensor? Stress tensor quantity is a quantity. In terms of if we would like to compare it with vector, then let us say velocity vector can be represented by a matrix of rank 1. Like this, stress is a tensor quantity and not a vector quantity, even though it has both magnitude and direction. Let us say as a vector can be represented by sum of 3 single basis vectors. That means let us say this I cap is a single basis vector, j cap is another single basis vector, and k cap is also another single basis vector. What it means, vector can be represented by a sum. This 1, 2, 3 sum of a single basis vector as follows. In the diagram you can see these are the x, y, and z coordinates, and I, j, k are the special types of vectors. Velocity vector can be represented by rank 1 matrix, as I have already told, but stress tensor cannot. Okay, it requires it needs matrix of higher rank than 1. Stress tensor matrix obey some transformation rule. Transformation, you can say, like what is the transformation? That means if you want to add one tensor, stress tensor. What is stress tensor? As I will show in the slide, this is the stress tensor shown in a matrix. This does not obey the rules of vector addition or vector subtraction. This is the main difference between tensor and vector. Stress tensor matrix obeys some transformation rules, but not rules like vector addition and vector subtraction. After that, matrix is a just array of numbers. Let us say we have different stresses with different magnitudes. Then matrix helps computation of stress components in proper manner. That means if you have to multiply this one stress tensor with another, then this array of stresses drawn in a matrix form, which will help us to solve the examples. Then what this sigma x, tau xy indicates, we will look here. Here you can see there are 9 components total in each direction, x, y here, and this is y and this is z, red line. There are normal stresses. That means on each face there is a normal stress perpendicular to each face, and in the tangential direction here you can see tau xy, and here tau xz is the shear stress. There are 3 normal stresses and 6 shear stresses. Don't worry, hesitate or get confused by looking this diagram. We will see the simpler diagrams. First of all, what are the positive phases? Actually, this is the smallest point or a particle in a material which we are going to discuss, or let us say keep in consideration. If we are applying a rod of cylindrical surface, then the very small point of cylindrical surface will be drawn here, or it is drawn here on this xy coordinate, xyz coordinates, and here we are analyzing it. This outer surface on the positive x-axis will be called as positive phase. Similarly, this one positive phase for the z axis, that is perpendicular to z axis, and here third positive surface perpendicular to positive y axis. Similarly, there are negative phases. Here you can see this is the positive x-axis from here to here, and here it will be a negative x-axis. So plane associated to this negative axis will be a negative plane or negative phase. Similarly, all these two also. Now, normal stress is acting on the x face of the element. Both these are x faces, this one and this one also. And you can see that here are sigma x normal. Sigma x means normal stress in the x direction, that is direction of x-axis. Here also it is in direction of x-axis. Here you can see, if there would be a vector, if stress would be a vector, then it should not have two directions at the same time. Simultaneously, any vector cannot be in the two direction. Vector have only one direction. But here you can see stress is acting in this direction. Same amount of stress is generated in this direction inside this component. Okay. Similarly, the normal stresses acting on the z face of the elements will be represented as sigma z. Here you can see sigma z, and on this face, the darken face perpendicular to this will be sigma z. Now, normal stresses sigma x, sigma y, sigma z can be compressive or tensile. If they are acting away from the center like this, away from the center, they will be called as tensile, and towards the center, if they are acting towards the center, they will be called as compressive stress. Now, how these shear stresses are denoted? Tau xy, shear stress acting on the x face of the element and in the y direction. X face means this 1 and 2. That means perpendicular to x-axis. That will be x face, and in the direction of y-axis. This one. Okay, this is the direction. Here you can see. The first subscript identifies the face on which the stress acting, and the second subscript shows or indicates the direction of stress. Here, second subscript is y. That means this tau is acting in the y direction, this direction. Okay. Similarly, tau zx and tau yz will be explained. Now, shear stress, whether it is positive or negative, how we calculate, or what is the sign convention. If the positive phase and positive direction is given in the diagram, then it is called as positive shear stress. Both, that means direction and phase should be of same sign. Here you can say negative phase and negative direction will generate positive shear stress. Either it should be a positive or negative, both positive phase and positive direction. Shear stress will be negative in case the phase is positive and direction is negative. That means positive phase, x phase, but direction is negative. You can see this. This is the negative y-axis. The stress is in the negative y-axis direction, and vice versa. If the phase is negative but direction is positive, then the shear stress will be negative. I think we will continue for the shear stress strain diagram, or SFD, shear force diagram and bending moment diagram. For discussing this SFD and BMD, we need to have some knowledge of engineering mechanics, formulas, and convention. Better, we will discuss this in next lecture. Just only see the types of support which will be used in finding out the SFD and BMD. These are fixed joint. Second one is hinge joint or pin. Then slider or roller support. These are actually supports: fixed support, hinge support, here again slider or roller support, and smooth surface.